also how you came to found the Climate Foundation.
Sure. Well, my background actually is in physics, planetary science, and engineering and applied science. And so I ended up going to Princeton and Caltech in those fields, worked at the Caltech Submillimeter Observatory in Hawaii for 3 years, started noticing things getting warmer even way back then, and then had 3 decades of work with Silicon Valley companies, designing systems on a chip, if you will. And we then around 20 years ago, we actually started working more on these climate issues. We did some expeditions across Greenland in a small plane, and we noticed these very small melt ponds that were turning into melt lakes. We actually connected with Professor Connie Steffen, who was leading glacier research at the time, and also with some NASA scientists that were looking at the satellite measurements of the melting of the Greenland ice sheet. And that was really profound because in the years that we were doing those expeditions, we found the melt ponds turned into melt lakes. The melt lakes got to be dozens of kilometers long and more than 100 feet deep. And by 2012, 97% of the surface of Greenland was melting during the summer. And that was really concerning. And that got us to think, okay, what can we do to actually address this problem? Well, there are 2 basic principles I knew: that it had to, ideally, we could leverage nature, the rest of nature, and its ability to fix carbon, absorb carbon, and remove carbon. And that would be essential. And that leveraging the rest of nature to do that in soils and seas would be key. And so we did some work in biochar, and the deeper approach actually has been regenerating primary production in the ocean and enabling that to thrive. So that's been a journey, and it's been a really interesting journey. We actually developed a climate house in Woods Hole, where we spent the 2010s in Woods Hole working with scientists and researchers there to really understand the root cause problems in the ocean associated with ocean warming and the challenges of algae and macroalgae, seaweed, and microalgae to keep growing. And so this is all about keeping our life support systems on ocean planet Earth running.
And so at the Climate Foundation, you're now running a number of experiments, I guess, pilot projects, to see if some of these ideas you have for accelerate what Seaforestation, I think, is a great term.
Well, I have to thank, I have to thank Paul Hawken for that in his book Regeneration. He has a chapter on seaforestation, and that was the inspiration for our public benefit company, Seaforestation.co. As part of our nonprofit Climate Foundation, we've got a stellar startup studio that we're using to actually build sustainable enterprises that can address these climate challenges. And really, our funders at the Climate Foundation have asked us to be catalytic with our projects, and that is develop sustainable enterprises that can continue to do the good work without requiring continual funding. They can fund themselves, and that's really the inspiration behind Seaforestation.
Well, perhaps you can take us through that, maybe starting at the high level, because I mean, one thing you're doing is you're helping to grow kelp, which is macroalgae, but I guess the first question is why are you doing that? Like, why doesn't just nature grow enough kelp and things like that? So give us a little bit of the background of, set us up for what the project you're working on is.
Sure thing. Well, I'll start with a slide from California, which is my home state, and something that, that's perfect. That really shows the situation from 2011 through 2015. And you might have remembered in the last decade, there was this big warm blob that came down from Alaska. That was a blob of warm water that actually sat off the coast of California. And that high temperature actually kept the nutrients from upwelling from the deep. And the net result was a lot less seaweed. As you can see on the right, 2008, the green dots represent where the kelp was off the coast of Northern California. And yet by 2014, we saw dramatic reductions in kelp. 90% of the kelp forest was gone. And so it's really a severe situation. And we've seen this trend over the past century. This big warm blob problem and associated El Nino is one that we've seen in the last decade or two. But the problem actually started way back in the 1900s. And that is, if you look at this slide on the right, this is a picture from the US Coast Survey, part of the US Geodetic Survey, or USGS. they had navigational charts dating back to the 1800s that actually show a kilometer-wide strip of kelp that existed in the 1800s. It was a hazard to navigation. That's how profound the kelp was. So we've seen these shifting baselines from the 1800s to the 1900s, where we've lost about a factor of 10 in kelp from siltation, runoff, reduced visibility, and all the rest in the water, which kept the juvenile kelps from growing. And then that coupled with a big warm blob and the El Nino. By the way, we're going to get another big El Nino next year. Yeah. So we're dealing with kelp on life support. And today the natural kelp forests sink and fix hundreds of millions of tons of CO2 just naturally. And so really we're asking, what can we do to reconnect the kelp forest with their deep nutrients and keep those ecosystems alive? They've been going for 20 million years or longer off the coast of California. And yet on our watch, in the last 300 years, we've wiped out 90% of them in Northern California and further south as well. And so that's where we got the inspiration for marine permaculture. And here's a drone picture on the left of a 1,000 square meter system that actually is growing kelp. In fact, there's a very little light dot. That's a Pacific green sea turtle that took up residence around our platform. It's about 2 feet in diameter for scale. And here's a small boat and some these other things. So the seaweed grows on this platform. It's a large ring, and we have red and green seaweeds growing there. But actually, brown kelps like those that grow off California can grow on these as well. And what we do, I'm going to switch to an elevation view, and that is at night we lower the seaweed platform below the thermocline, below the nutricline. It's about 120 meters deep, where the seaweed acts like a sponge and absorbs nutrients all night long and concentrates nitrate, phosphate, micronutrients right in the tissues of the seaweed. And then at sunrise, we lift the seaweed up to the surface, and it absorbs sunlight and carbon dioxide in the top meter of the sea. And it's the combination of the deep nutrients and the surface CO2 that provides net additionality for this process.
And why isn't that natural anymore? Because obviously over 20 million years, you weren't there to help lower it down and put it up. So it used to work before. And what's broken?
Well, before ocean warming, an offshore wind like a Santa Ana would be enough to bring those deep nutrients up, and the kelp would do fine and be irrigated in the deep nutrients. But an ocean warming situation puts an energy lid on the top layers of the sea. It's warm water, but it has zero nutrients. So unless you can punch through that energy barrier, you need more and more wind to do that. You're getting far less nutrients to the surface, and that's why the kelp forests are being devastated.
So the kelp used to be growing up above where both nutrients and sunlight, and now it's just sunlight. So now you're moving it down below to grab nutrients and then put it up during sunlight.
That's it. Yeah, and some people have tried upwelling, but I think this approach scales faster. It takes 100 times less energy, and it has a greater degree of social acceptance. So we find it's a good approach overall.
Okay, very good. Tell us more, because what the benefits of doing this are, besides the kelp is happy, but
well, we produce a lot of food, feed, and fertilizer because we sustainably harvest. And while we're doing that, I have a schematic that shows this. So we have a platform growing here on the left, and we sustainably harvest that platform, and it goes through a biorefinery where it produces liquid biostimulant. And I'll show you some of the benefits of that briefly and shortly. But it also produces dry pulp, and that dry pulp is used today as food ingredients. If you have your toothpaste or your ice cream, it tends to have seaweed carrageenan in it. And so these food ingredients, it's already a multi-billion-dollar industry. But in addition, it provides a really good feed supplement. If you feed seaweed to cows, they can reduce their enteric methane emissions for ruminant livestock. And it's also great for aquaculture because you've got omega-3 fatty acids in the seaweed. So if you feed it to chickens, you'll get omega-3 eggs, and if you feed it to cows, you'll get omega-3 dairy. So that's a nice benefit there. Furthermore, a fraction of about a quarter of the seaweed that's growing on the platform falls off the platform during growth and sinks 1,000 meters a day to the deep seafloor, where it can remain for centuries, or in some cases, even 1,000 years. And that represents a true blue carbon sink. And so we end up having emissions reductions associated with agriculture. We end up having carbon removals associated with the seaweed growing process. And surprisingly, there's even a climate repair dimension to this. And I want to tell you about our afternoon with Sir James Lovelock a couple decades ago in Silicon Valley.
Well, I definitely want to hear about that. But before you go, I mean, let's to be super clear.
Yes.
Emissions reduction comes because you are growing cattle and chicken feed in the ocean, and therefore you are avoiding deforestation. Is that the main benefit for
no, actually, it has directly to do with fertilizer. So here's an example of our growing rice with and without the seaweed foliar biostimulant. Mm-hmm. And without, you get 80 to 85 centimeters. With, you get 110 to 120. And that's with less fertilizer. And that's what's amazing, is that we're able to actually, well, here's our 2025 results. This is a government-run trial by the Philippine government. They did 2 trials, and they said, okay, if you do nothing, you get about 2.5 tons of rice per hectare. If you just add the normal fossil fertilizers, you get 4.5 tons, which is pretty good. If you add both, that's this 4th column here, you get fertilizer and the big grow biostimulant, you get over 5 tons. But the thing that blows away is you just add the big grow biostimulant and nothing else, like you eliminate all the fossil fuel fertilizer, you get almost the same result, over 5 tons. So we can reduce or eliminate a lot of the fossil fuel fertilizer. Those avoided emissions has a dramatic effect. In fact, we've studied for the last 3 years what we call the fertilizer specific yield. And that is the number of sacks of rice divided by the number of sacks of fertilizer. And that's 2 to 6 times higher for these blue trials relative to the orange controls in both 2023 and 2024. And we see the same results this year. So that's the avoided emission, is less fossil fuel fertilizers. You know, the price of fossil fuels, you know, with the war going on, is going way up, and the price of fertilizer is going way up too. So how do we address the farmer needs of reducing costs or maintaining costs while at the same time maintaining or increasing yields? That's what this addresses.
But so you're not even taking into account the avoided deforestation, because that would be huge.
You know, that's
fed cattle and chicken that would otherwise be grown in the Amazon, let's say, has tremendous environmental damage.
It is huge. And I think I've got to point to George Monbiot, who in the book Regenesis discusses precision fermentation as a vegan way to produce protein. And when you do that, you can probably feed 10 billion people with replete protein using, according to George, 70 times less land area than we're using presently, which would enable rewilding of most of our forest and pasture land, which would provide habitat for 8 million species.
Yeah, although, you know, I think people won't feel as happy about eating kelp. I mean, maybe in the future, maybe we all will, but in the short term, they don't mind if cows eat it and chickens eat it. So,
well, you're eating it today when you have ice cream.
Yeah,
your toothpaste.
That's true. So, very good. So, all right. So you're doing this. You're stimulating the growth of kelp. We just discussed some of the benefits of reduced emissions through fertilizer and perhaps through less deforestation. But then you also mentioned that some of the kelp falls off the platform and sinks to the deep. And so tell us a little bit about that carbon sequestration aspect of what you're doing.
Definitely. We've been doing a 2-year carbon cycling study with some of our colleagues at universities. And I'm just looking for a relevant slide there. Here it is. We've been, our colleagues at Princeton University, Scripps Institution of Oceanography, Rutgers, and National Taiwan University, we were doing a 2-year carbon cycling study to measure the carbon cycling under the platform on our 1,000 square meter platform in Cebu, Philippines. And we've been using a variety of experimental techniques to do that, including the use of an underwater glider to measure the nutrient levels, oxygen, nitrate, and phosphate, sediment traps that can actually accumulate the seaweed as it's falling and measure what the flux of seaweed is per square meter. And we're using drones to actually measure the daily growth rate and the fall off rate of these seaweeds from images that we can actually use to train large machine learning models to actually predict the daily growth rate and the daily fall off rate of these seaweeds. So between that and the plankton toes, this has been a great array of experiments. We're looking forward to completing our data taking and publishing those results in the months ahead. And we're enthused to use these data as the basis for really developing normative standards for carbon removal that ultimately we'd like to include in CORSIA standards and other kinds of standards for reducing emissions for airliners and things of that sort.
Yeah, so the people don't appreciate, but when you have some way to reduce carbon, one of the most difficult things is measuring it. So the fact that I'm glad you're focusing a lot of effort on how to measure how much carbon is actually being permanently removed from the system.
That's a great point, Dan. And that's one reason that we applied to the Bezos Earth Fund for a small project to really get started on developing a machine learning benchmark on taking drone images and using those to lower the cost of monitoring, reporting, and verification, because it looks, I mean, it's very expensive to deploy these systems underwater. But with that ground truth data underwater, you can couple that with the images and now develop a training set for training machine learning models to recognize this. And flying a drone out there is about 2 orders of magnitude cheaper than deploying one of these gliders. And so that ends up being really attractive.
And I think this should be very clear to everyone. So what's happening here is you're growing a plant, kelp, and it's made out of CO2 that it gets from the air and from the ocean, but the ocean and the air are sort of matching each other in levels of CO2. So if you take some out of the ocean, then more comes from the air into the ocean. So it's still taking CO2 out of the air. But of course, normally a plant dies and then releases its CO2 back to the ocean or to the atmosphere. And then, so it's all neutral, carbon neutral. But if you can take something and you grow it and then you have it sink to the depths of the ocean and it's deep enough, it's going to stay down there for a really, really long time, hundreds to thousands of years, depending on how deep it is in other situations. And so basically you've now removed CO2 from the atmosphere by growing plants and then sinking them down there. So that's what that's what you're doing here.
Yes, it is. In fact, there's a very interesting thing. When that seaweed hits the seafloor, if there are calcium carbonate sediments in the seafloor, it'll dissolve some of the calcium carbonate and form calcium bicarbonate. And that's dissolved in the ocean. That stays in the ocean for 100,000 years. So it's a great long-term tail, if you will, to the carbon removals. So that's the second thing.
There's another way to take carbon out of the atmosphere is using weathering of rock, which is sort of does the same thing. So that's
this will do it without
you're combining techniques.
Yeah, it is. Well, the nice thing is you can get this calcium bicarbonate without having to mine anything or put anything in the ocean. You're actually using the calcium carbonate sediments, which are present from 1,000 to 3,000 meters deep.
So to summarize so far, we have a platform that reduces emissions through fertilizer and, again, I think through deforestation. And so that's one. So the three things we have to do for climate change, there's actually four, but the three things we have to do are we have to reduce our emissions to zero, by the way, as fast as we can. We have to then remove all the excess CO2 that we've already put in the atmosphere, 2.6 trillion tons. And then the third thing we have to do is cool the earth while we work on the other two things, because it's already too hot already. And by the way, the fourth thing we have to do is to adapt to the climate impacts that are already here and going to get worse. So those are the four things. You're working on three of those four things, but we mentioned already about how you're reducing emissions. Mm-hmm. We just spoke about how you're actually reducing CO2 in the atmosphere through that process of the kelp falling to the ocean bottom. But there's a third aspect, because the title is Seaforestation Can Reverse Climate Change. At least, a little provocative perhaps, but there's a third aspect of what happens with your system that actually can cool the planet. But can you tell us about that?
Yes. 2 decades ago, I had, at the invitation of Armand Neukermans in Silicon Valley, he said, "Come on over, James Lovelock's here." And it's like, well, I'm just finishing reading The Vanishing Face of Gaia and
I don't know. By the way, I'm not sure everyone knows who James Lovelock is, but he saved your life. He figured out that there was an ozone hole back when there were no instruments measuring anything like that. And he convinced folks and that other people joined him and figured out, yeah, you're right. Oh my God, there's an ozone hole. And we did the Paris, the Montreal Protocol, which reduced the chemicals that was destroying the ozone. If that thing had continued to break down, it increases cancer rates and does all kinds of nasty things. The ozone layer in the upper atmosphere protects us as a shield. That's one of the things he's done. He also is very famous for his Gaia hypothesis, which says the Earth operates as if it were a living being. It can regulate the amount of CO2, its temperature, and things like that, just like our body can regulate its temperature and other things. And he lived to be
100
years old and died it was fairly recently. But
yeah, at the tender age of 99, he wrote the book Novacine, which is about humanity coexisting with our silicon offspring in a bountiful, cooler world, which is, I recommend it. It's a really good book.
But and before you go on and tell us what your interaction with him, I'll tell you one story about him, and that is about 20 years ago. This reporter came to interview him. A famous guy who worked on all these things, and he was talking about climate change and what's going to happen. And this kind of freaked out the reporter, hearing all the terrible things that are going to happen. And he said, "Well," he asked James Lovelock, "Well, what should I do? What should we do?" And James responds, "Enjoy the next 20 years." So
incredible. Well, I'm not quite as fatalistic as that.
Well, I'm just saying that's a famous James Lovelock story.
Fins in the water. What can we actually
tell
do?
Us about your experience with him.
Well, James pointed out that about 1 billion years ago, algae discovered dimethyl sulfide. And as you know, James is a chemist, an atmospheric chemist, among other things. The dimethyl sulfide was very useful to algae because they're living in the seawater. You've got all these ions in the seawater that are actually blocking a lot of important biochemical reactions in the cell. And dimethyl sulfide balances the osmotic strength of the ocean water with zero ionic strength. And so what it means is the dimethyl sulfide can enable the biochemical reactions to occur while establishing the salt balance, if you will, across the membrane of the cell. Well, that's great, but it does something else. When the cell dies, that dimethyl sulfide is a gas that goes across the air-sea interface, it goes into the atmosphere, and the ultraviolet light converts that DMS into a small sulfate particle. And that small sulfate particle contributes to marine aerosols, marine cloud brightening. And what happens is those aerosols go up to the bottom of the clouds and actually enable clouds to condense. And so those marine clouds that I was showing end up being very significant. And James's thought is that these algae actually brought about the cryogenian period of the Earth, which lasted for 115 million years, that it was too much of a good thing. And you had high latitude algae, more and more clouds, more and more ice, cooling things off. And it resulted in the sea ice marching further and further south to the point where we had glaciers in Ecuador at the equator. This is in the geologic record, right? And for 115 million years before the Precambrian explosion, we had snowball Earth with just a few polynyas near the equator where the algae was eking out a survival. And we had to wait until it was 50 or 100 million years for the volcanoes to emit enough CO2 to actually overcome this incredibly powerful biological effect. I like to say life created the Earth in its image. And what I mean by that is the distribution of elements across the biosphere is largely determined by life. And this is a very strong version of the Gaia theory. And that is that the algae actually brought about its own ice age and snowball Earth. It took 115 million years to recover. When it finally did recover and we drew down enough, we had enough CO2 to get out of a snowball Earth situation, we had the Precambrian explosion, of life. Ever since then, we've been drawing down CO2. And we've gotten into the periodic ice ages of the last million years, but we just canceled the next ice age. And now we're going back towards, the Earth system is stable in an ice age, as it has been over the past million years mostly. It's also stable as an ice-free planet. But the problem is the ice-free planet may only have enough primary productivity to feed 1 billion people. And that would be a major concern.
And a lot of other problems if we were in that world.
There's so many problems. And so, what's interesting, I mentioned this because James Hansen, Professor James Hansen at Columbia, I think has said something, I'll paraphrase, our organizations have grossly underestimated the sensitivity of the Earth system to greenhouse gases, and grossly underestimated the sensitivity of our Earth system to aerosols. Mm-hmm. And we really need to turn up the gain on both of those with our IPCC models, et cetera, to really accurately portray what he says. Look, the emissions we've done already, 4.8 degrees Celsius plus or minus 1.2. And that's just based on the greenhouse gases and the geologic record that show over the past million years, the Earth's sensitivity. And we need to pay a lot more attention to aerosols because, if you look at the historic temperature record in America and Europe, it kind of goes flat for a while, and then it hockey sticks up at right around 1980. Well, 1980 was when they passed the Clean Air Act and cut aerosols over land. And now with the International Maritime Organization in 2020, we saw a massive cutting of aerosols over the ocean. And surprise, surprise, we had huge wildfires just a few years later in Hawaii and most recently Los Angeles. And is it really, nothing related to the cutting of aerosols? That's a really important question. And just last year in January, Panama suffered its first failure of its upwelling on the Pacific coast. And that's right near the Panama Canal, where all those ships go. But that failure of that upwelling means far less algae growing and a collapse of the sardine and anchovy fishery, which is vital to the economy. So we're seeing these economy collapses that are really critical. And fundamentally, it's a problem of what Tom Chi likes to say, all of our economy is embedded within ecology. And so for us to get serious about sustainable economy, we have to think deeply about sustainable ecology. And that's essential to anything we do going
forward. Economy is a wholly owned subsidiary of nature. That's
exactly.
And people think that, I just saw today, the deniers are still out there in force. And one was saying, well, the Earth, it used to be a lot warmer, so there's no problem with that. Like 400 million years ago, it was a lot warmer than today. And people kind of forget that, was it 2008, when subprime mortgages defaulted, something no one had ever heard about before, right? Some little minute thing in the financial system kind of went haywire. It brought down the entire economy. Now take something fundamental like, oh, by the way, your city has no more water, or you can't grow the food you thought you could grow anymore. These things, people don't realize that everything is kind of nicely balanced and just working, and you can pull one card out of the deck of cards and it's all going to come falling down. Now take 25 at the same time and see what happens.
That's so true. And so fast forwarding 1 billion years, how can we use this knowledge about the profound effect that algae has on the ocean and the atmosphere to actually address some of the problems we're facing? And I think that problem can be well seen with the slide that I've got up. If you can share. And that points to the NASA.
Let's try this.
Right. The NASA Ceres satellite has actually measured that we're on a dimmer and duller ocean planet Earth than just 20 years ago. And this is also measured by the Big Bear Solar Observatory, which measured the dark side of the moon, where it reflects Earth glow. And that is the sun bounces off the Earth, hits the dark side of the moon. You can measure that brightness, and that will tell you how bright is ocean planet Earth today. And over the past 20 years, we've seen a loss of 2 watts per square meter in visible sunlight, as our planet has fewer of those marine clouds that are well depicted here off the coast of California. And so these marine clouds, their extent, their duration, their brightness is vital to keeping our coastlines cool. And there are tens of millions of people living within 100 kilometers of the coastline. And these clouds get all the way into Livermore, all the way in towards Riverside, Southern California. It's really profound. And what we'd like to explore, and we're hoping to raise funding for, is our rebrighten.org project, which is an effort to take our seaweed rings and actually measure the biogenic gases that we talked about, the dimethyl sulfide, mercaptan, and isoprene are two other gases that actually come off the seaweed. They form gases above the seaweed, and they actually produce cloud condensation nuclei. And those with a normal convection get up to the base of the marine cloud layer and actually contribute to the brightness, extent, and duration of those marine clouds. And so we can use our kelp forests. I like to say, Mark Twain said the coldest winter that he ever spent was a summer in San Francisco. And that may have been because of the extensive kelp forest that existed in Northern California in the 1800s and is absent today. So that's a key aspect. We've made proposals to NASA to work on this, but they haven't gone through yet. And so really we're looking for private support to support this rebrighten.org project that can address this issue and potentially also address submicron sea spray. You may notice here that we've got great sea spray on the shoreline, the hazy beach atmosphere that you can see as you look up and down the coast is partly due to this sea spray. And there's been 30 years of research that submicron sea spray can be a great alternative to rebrightening those ship tracks that we've lost because the fossil aerosols are gone. We're not proposing to bring them back. But submicron sea spray and biogenic aerosols from kelp, those are two areas that are really promising to rebrighten our coastlines and really address at a local and regional level with full transparency an opportunity for residents to actually protect their economies, their livelihoods, and their communities from excessive heating. And of course, a cloudy day is 20 degrees cooler on the coastline than a sunny day.
Wow. Yeah. And of course, there's a lot of work separately from what you're doing on marine cloud brightening and how to, send pulverized seawater up into the air to try to form clouds. So there's a lot of interesting work. One thing, by the way, have you looked at nanobubbles and things like that? Because you could actually have a little around the outside ring. You could be generating nanobubbles and cooling and basically what that's like the white foam when a wave crashes. Mm-hmm. And that also reflects the light. You could do a little extra in between the circles. You could do a little more.
I think it's great to do that. Also with shipping, that it's quite likely that microbubbles and nanobubbles can reduce the drag on shipping while at the same time rebrightening these tracks with brighter seawater that could last for a longer time. And so these are areas that we need to research. And I think there's a great opportunity for private as well as public funding to really investigate these areas. Just like we do clinical trials in medicine, this is an opportunity to do those clinical trials and determine the benefits and any side effects well before it's needed as a prescription drug to keep our civilization alive while we rebalance our carbon budget.
There's a guy named Russell Seitz who did some initial work on nanobubbles, and the key to making it a climate solution is you can make nanobubbles very easily just using a jacuzzi jet. But the thing is, they don't last very long. But I'm just thinking about this just now. One of the ways you make them last longer is with surfactants, like soap, basically.
Yes.
But one of the places that was suggested to get this material that will make them last long is kelp. So there may be some little built-in thing here that combines together to get you these long-lasting bubbles that would make and basically what you're doing is you either have a ship, it just makes these little bubbles behind it, and if they last a long time, you get this white foam on the, which again, very natural thing. It's there all the time, and especially near the shore where the waves are crashing. But even in the middle of the ocean, you get waves that crash, and they cause this little white foam, and it reflects the sun. And if you do that enough,
that's a great point.
You have another way to reduce the temperature of the Earth.
That's right. That's a great point, Dan. It's an opportunity. It turns out the biofilm, the reason we get sea foams is that the algae produces biofilms, and those biofilms actually act as a surfactant and keep the bubbles alive much longer than they would be otherwise. So these are examples of local and regional approaches to all three legs of the climate triad that we're interested in engaging with communities up and down the coast on both sides of the Pacific, by the way, from Australia and the Philippines to the coast of California. And we've raised half of the funds needed for America's first pilot marine permaculture project off the coast of California. And if we can match those funds, it's around 300K, we will greenlight the project and build America's first pilot ring of kelp.
Well, actually, I know some people that kind of fund this kind of thing, so we'll maybe make some connections there. But let's talk a little bit about the scale. Okay, this is great. You have this thing going here. You said this is how big is this one, the picture?
1,000 square meters, but we're up to 2,500, and later this year we'll have 10,000 square meters as a baseline commercial scale platform.
Okay, so how big does it have to be to, first of all, to reduce emissions by, let's say, a gigaton?
Well, 1 square kilometer can remove or avoid 30,000 tons of CO2.
So that's combining, sequestration and avoided emissions. Is that correct?
That's right. We've got about 8,000 tons of carbon removal, 12,000 tons of reduced fertilizer manufacturing, and 10,000 tons of reduced nitrous oxide emission, because 20% less nitrate on the soil means 20% less nitrous oxide in the atmosphere.
Okay, and then that's not sequestration though.
That's avoided emission.
Oh, avoided. Oh, I'm sorry. Oh, avoided emissions. Okay. Okay.
Exactly.
This is not sequestration yet. Okay. And is there another slide for how much it sequesters? How much?
Well, the sequestration, it's on the order of 8,000 tons per square kilometer per year, and so that's that is the quarter of seaweed that falls off the platform during growth. And so that ends up being about a quarter to a third of the total amount.
So for this thing to have an impact on climate, let's say, you know, a gigaton, you know, we emit 40, 50 gigatons, depending on whether you're looking at just fossil fuels or other things, but roughly in that order, 40 gigatons a year. So knocking off 1 out of 40 is a good thing. Of course, we'd want something that knocks off 40 out of 40, but to get up to 1 out of 40, how big does this have to be?
Well, it ends up being around 35,000 square kilometers, which is about 0.3% of the U.S. exclusive economic zone.
Yeah, people don't realize that. The United States itself, including Alaska and Hawaii, is only 1.9% of the surface area of the globe. So yeah, so this is actually much smaller than people think it is. And you can compare it to anything like the area used to grow corn for ethanol. It's like I think a lot bigger. We'd have to look that up.
It is.
And then things like that. So, and how do you scale it up? What's the process? Okay, you have this. How expensive is it, for example?
Right. Well, we managed to lower the cost 5 years ago with the R&D costs and whatnot. Building one of these platforms would cost millions. We've gotten it down to just a couple $100,000 to build a hectare now. And as we build 100 of these hectares and more, we'll get it down to tens of thousands of dollars. So this is coming down in cost. And of course, the offtake for food, feed, and fertilizer, well, these days, the price of fertilizer is going to be doubling because the fossil fuel price went up so much. So, you know, unilaterally, I think some of the attacks going on in the Middle East have probably reduced natural gas by about 20%, given the number of trains that are taking place there, and the number of reduced emissions. It's had a profound effect on the climate. The faster we can reduce our dependence on fossil fuels, the more stable we can make our economy. And I think one thing that's important here is to emphasize, at a hectare scale, a coastal community can run and operate one of these platforms sustainably. It's a local and regional intervention. It provides job security, it provides climate resilience, but it also potentially addresses this third leg of the climate triad locally and regionally. And that's where I see the frontier of climate repair, is with community-led projects to do local and regional climate repair to keep their communities cool. And this can be done with marine cloud rebrightening. And that's the thesis behind rebrighten.org, which was co-founded by the late, great Professor Stephen Salter of Edinburgh University, who dedicated more than 30 years of his life to these kind of solutions. And I think at local and regional scale, it's a huge opportunity. When it comes to regenerative economics, it's what we can do at community scale. And that's where individual actions can really make a difference. And that's one reason we did a webinar last week down in Santa Cruz. It's a great opportunity to regenerate coastal communities. But of course, these effects go hundreds, if not thousands of kilometers inland. One of our advisors and directors, Ray Schmidt, is a researcher at Woods Hole Oceanographic Institution. And he actually discovered that rainfall in the Midwest was better predicted by sea surface salinity in the Caribbean than by El Nino. And so there's more variance, and actually measuring that evaporation, the rain that, evaporates in the Caribbean, falls in Texas. The next day it evaporates in Texas and falls in Oklahoma, and it works all the way up to the Dakotas. So that ends up being a profound effect on really understanding that hydrological cycle each day and how profound it is. And that's why I think decentralized, even community level interventions are something that people can get involved with and really be part of the solution when it comes to building healthy communities with abundant energy, food, labor, and a good climate.
So have you worked out the economics in terms of avoided emissions and also sequestered CO2? Like what, not now,
yes,
but like when you're at scale, when you're lower.
We're doing a life cycle analysis presently with the Department of Energy, Argonne National Laboratories. And it turns out if we include the revenue streams of food, feed, and fertilizer, the cost of carbon can actually be negative. And that's because the system pays for itself, and we can document that carbon removal with our affordable MRV technologies like drones, taking a picture like this one on the left, showing the seaweed daily growth rate and fall-off rate. And with those calibrated measurements, we're able to actually have a negative cost of carbon removal when we consider all the revenues that take place.
And can you kick off like extra kelp, like have little things that go around cutting off more of them to accelerate, to increase the amount of sequestration versus avoided emissions? You can kind of.
I will say this: once we've taken care of our food, feed, and fertilizer needs, and we have, we're feeding 10 billion people, and taking care of those 8 million species, yes, you can grow more because these platforms are designed to work in all parts of the ocean greater than 100 meters deep. And that means, there's between where I am, where you are now in California and my home in Australia, there's 10 billion hectares of mostly empty subtropical ocean that are accessible to marine permaculture. So as far as scalability, there's really a huge potential.
First, and I don't know the details, but I thought for sequestration, we have to be like really deep, like 1,000 meters.
Oh yeah, but that's the nice thing about deep water. I mean, the seaweed drops about 1,000 meters a day. So in 24 hours, it's down to a depth where the sequestration time is centuries to millennia, according to many of the peer-reviewed studies. There's a wedding cake image that at the bottom of this slide that shows the time scale, 10 years, 100 years, 1,000 years, as you go down 300 meters and 1,000 meters.
So but how far does your platform drop though to pick up the nutrients?
We just go down usually 100 meters off the coast of California. You might even go down 70 or 80 meters, but in the Western Pacific, where you've got a lot more warm water, we go down 130, 140 meters to get enough.
But the nutrients are there, but then below that is another 700 meters or whatever or more of room to the bottom.
That's the skin of the apple. And these systems are designed to work in deep water. The average depth of the ocean is 4,000 meters. And down there, you're talking about the bathypelagic. You've got sequestration times. I mean, the water off Australia has to get all the way to Canada before it can upwell.
Okay. So what's next? So you're trying to raise money, and you're building this bigger platform. Tell us, what's coming up in the next year or two?
Well, we've just imported our first case of Big Grow seaweed foliar biostimulant into California. And so we're looking for people that want to try it out in their backyard gardens, in their horticulture, and in broadacre agriculture. It costs about $10 a hectare, that's 2.5 acres, to crop dust and apply a biostimulant or other kinds of amendments to broadacre farmland. If you use a drone, it can be less than $1 per hectare. So it's 10 times cheaper, and it's something that can be applied broadly. And quite frankly, imagine, 1.5% of all energy used on the planet goes into making nitrate fertilizer. Imagine if we could cut 20, 50, or 80% of that fertilizer, while at the same time boosting yields double digits. That's the potential to apply to all the farmland in America.
So you mentioned that this could make money. So when something that can make money, instead of going after grants, I mean, you need the grants because you're testing things and it's not really commercial yet,
Sure.
but eventually you could go for venture capital or go to the big food companies and get them to fund these kinds of things.
Well, it's true, and that's the idea behind our nonprofit Stellar Startup Studio, is to really be the golden goose that lays golden eggs, and those golden eggs are sustainable. And one of them is Seaforestation.co. And so the intent is to build this, to build the value chains that really demonstrate the lasting value that can actually build a healthy industry that can enable thousands of communities along the coast and beyond, and in agriculture as well, to really thrive in spite of climate disruption and in spite of high oil prices.
Okay. I don't know if Stacy's ready, but Eli's here, and I want to thank Eli for also helping to arrange to get you here, Brian. So let's have Eli. Hey, Eli, welcome. And how you doing? And what's your question for Brian?
Hi, thanks. Great. So I'm wondering what you think might be the ultimate limit. How far could we go in terms of, how many tons or gigatons of carbon dioxide could we remove and sink per year if there were no obstacles in the way, you had everything you needed to go as far as you wanted?
That's a great question, Eli. There are two sources of deep oxygen in the ocean, and one of them is the Southern Ocean near Antarctica, where there's enough oxygen for about 5 gigatons of sequestration each year near the seafloor. And the amount of oxygen going into the deep ocean in the Atlantic comes from the Labrador Current, which is about another 5 gigatons worth of oxygen that could actually contribute to converting carbohydrates to CO2 at depth. Beyond that, there are special basins like the Santa Barbara Channel and the Black Sea that are anoxic. And when you drop carbon in those anoxic basins, you can add additional gigatons that doesn't ever oxidize. It just, for a long time, it just stays down there as fixed carbon. In fact, you can look at old ships in the Black Sea that are thousands of years old, and they're still intact because there's no oxidizing bacteria to decompose them. So we've got those, images on the seafloor already. And so that's a great example of where you can do. So that's on the order of a dozen gigatons that can be identified as sustainable, as long as the Antarctic bottom current or bottom water continues to be produced. Of course, as it gets warmer in Antarctica, that life support system may be diminishing, just as we've lost about 30 to 40% of our primary production in the subtropical Pacific Ocean just over the past 60 years as well. So we've got to get back to where we were pre-industrially. That's key. We like to say if we can triple the area under deep water irrigation each year for the next dozen years, we can reach a gigaton of carbon fixation in the 2030s. And so that's a good initial goal. And then by then we'll have plenty of knowledge on the speeds and feeds and what's sustainable in the deep ocean in a decentralized way that can enable us to determine how many gigatons as a society we want to do that way versus other methods.
So a couple of things. We're only just in the last decade starting to learn about the ecology of the abyssal plain, what lives on the seafloor. We used to think that there wasn't much of anything down there, but in fact there is. Do we have a good handle on what the ecological impact on those ecosystems, which are generally out of sight and out of mind, would be at the scales? Do those possibly make the safe limits lower?
Great question, Eli. And there are a couple of data points on this. First, you have to understand that with decreased primary production of 30 to 40% in the Pacific Ocean now, you're looking at far less marine snow falling down, which means less food for those benthic communities. So they're suffering right now from decreased food supply and not decreased oxygen. So the first challenge is just get back to pre-industrial levels of primary production, which can support fisheries and support those benthic communities. Once that's addressed, then certainly measuring the deep oxygen level and monitoring that will be useful. That's easy to do with the gliders that I showed earlier today. And it's something that we need to monitor as we go forward, because there have been some challenges to the Antarctic bottom water formation in recent years, because Antarctica has been getting so much warmer, and there's been a lot of fresh water melting, off the sea ice, off the glacier ice, I should say. And the result is that fresh water can put a cap on top of the formation of cool water off Antarctica. So we need to monitor those things. But today, it's a problem of just getting the food supply back to those benthic communities. And that's the biggest challenge that I would say they're facing today across the Pacific Ocean.
And finally, what if you could name, one thing that would be rocket fuel to these efforts, what would that be?
Well, I would say it's really engaging community efforts to really ensure a food supply. And I think a lot of it is a public awareness of the profound changes we're going to see in our lifetimes on the impacts of climate disruption. The temperatures are going up. We're seeing wildfires already. We've got to make those connections and really understand that climate repair is an essential part of our recipe to keep our civilization on the rails, because we've delayed. It's been a third of a century since the Rio Declaration in 1992 by Jacques Cousteau and 170 world leaders, that in Section 15 say, do not let scientific uncertainty be a cause for inaction when it comes to taking scalable climate change interventions. And so we really need to use all three legs of the climate triad. They'll be absolutely necessary, because we know it'll take decades to get our emissions to zero and to actually do the carbon removal. In the meantime, the climate repair is going to be absolutely necessary for us to keep our civilization on track, 10 billion people fed, and ideally rewilding some habitat for 8 million species to ensure our ecosystems can continue to survive, so that our economy can continue to survive. So those are essential aspects to making that work.
Very good. Hey, let's bring in, let's go here and let's bring in Stacy. Oh, wait, go to here. Hey, Stacy. Oh, you got to turn your mic on. No, you're muted.
Sorry about that.
There you go.
Hi, Dan. Hi, Brian. So
Hi,
good to
Stacy.
see you. And great to hear about your work more fully after hearing just bits and pieces for years and years now, since back in the Clubhouse days.
The future's here today. It's just not broadly distributed yet.
Yes. My question, there's also one in the chat that's somewhat like it, is, and I think the answer is pretty easily, yeah, it's all cool. But I know that people get up in arms about mining or doing anything that disturbs the sea floor.
Mhm.
You're just helping nature along, doing the things it was doing. It's not going to disturb sea life, or it's only going to help. Is that right? For us and them.
That is correct. I mean, we are monitoring the heterotrophic, plankton and fish and everything that's going on downstream. And that work is in conjunction with Scripps Institution of Oceanography in San Diego. And so we do monitor for those things. Right now, it's important to understand that when you lose a third of all the primary production in the ocean, in the subtropical ocean, that's less food, that's less habitat. Just getting back to the pre-industrial levels will require, thousands of square kilometers just to address that challenge. Now, we can do it with seaweed. The nice thing about seaweed is you can hold on to it. And so you can actually use it to produce products as well as nice habitat and fish feed. And so let's just get back to pre-industrial levels, and then we can have that conversation about, okay, well, how much do we want to increase that process? Getting back to pre-industrial is a good goal. Same on temperature. Like, let's just get back with our climate repair. Let's just get back to pre-industrial levels of marine cloud brightness, so that our coastlines can continue to be, cooled while we're actually getting back to, let's say, pre-industrial levels of cooling.
Yeah, after having our heat wave here last week, I appreciate that. Um, the other thing I wondered is, I know, of course you're raising money. This, costs money to do this work. And yes, the research phase would cost more than when you're actually at scale deploying things on the regular. Do you have this sort of parsed out? All I can think of is like Sally Struthers back in the day. For the price of a cup of coffee, you can feed a child, that kind of thing. Do you have like a price for a price of a what? You can build one of these permaculture gardens.
Well, we've actually done a sort of innovative approach, and that is we've developed a kelp coin to actually model the life cycle of a marine permaculture. And so instead of minting a coin, we grow a coin. So you buy an immature coin at the start. It takes 48 months to grow. We have third party verify a ton of kelp that's actually been grown. And then it's tradable on a secondary market, which we're establishing this year. And then at the end of the cycle, someone can either sink the coin or purchase a coin and sink it, and at which point we verify a ton of additional seaweed representing a ton of additional carbon dioxide that's been sunk to the middle and deep seafloor. So,
oh gosh, now I'm concerned because that's the kind of thing that it sounds like subprime mortgage stuff. Like it's like, oh my word, it's an instrument, and I have to think about how this works versus just tell me it's $1,000 or 10 or 100 or something. But anyway, I know that's all the rage right now. So.
Kelp coins are only $250 today, but they represent a true blue carbon sink. But they represent more, and that is it's an investment in living ecosystems. And I think a living kelp forest with living fish is probably more valuable than the carbon on the seafloor. But they're both important.
Yep. No, agreed. So is Leon going to go?
No. Let's go through the questions.
Okay. So the Robbie, this is the first one, Dan said, how has global warming affected the boundary between warm and cool ocean currents where kelp grow?
Well, that's a great question. There are two kinds of currents. There are, of course, we see things like the Atlantic Gulf Stream, which is concerned about, shutting down to some extent. And that's certainly a problem, both horizontally and vertically. But there's also this warm layer of the ocean that we've talked about where, the rate of ocean warming has more than doubled with a decrease in marine clouds. And we've seen more than 1.5 degrees of Celsius of warming in the surface ocean today. And as I was highlighting earlier, life in the ocean depends on the deep nutrients getting up to the surface in order to have the nitrate and phosphate that we know is needed to grow these algae. And so when you have a lid on your ocean, it presents a bigger and bigger energy barrier to those nutrients. And we know how this ends, both 50 million years ago with the PETM and 250 million years ago with the Permian mass extinction. Though there was a carbon pulse, the air got very warm, the ocean got warm, it stratified, the oxygen levels dropped, the nutrient levels dropped. And when the oxygen got low enough, we lost 96% of all marine species. So that's business as usual. And what we need to do is reconnect the algae with the deep nutrients, keep that life cycle going, and enable a different outcome. And it doesn't take all that much effort and energy to do so, but we need to wake up and realize we need to keep our ecosystems going. We find time and time again, give nature half a chance and she'll rebound exponentially. And we see that on our platform. As soon as we got our platform running, we got thousands of sardines, hundreds of tuna, dozens of dolphins, families of dolphins spent months around our platform enjoying all the ecosystem services there. And we even had 2 or 3 whale sharks show up and eat some of the algae as well. So it's, nature has voted with her fins. We said, you've got the good stuff, and game on. Let's regenerate life in the ocean while we're actually repairing our climate.
So you're a marine developer is basically it.
Sustainable development. This is so many of the aspects of our polycrisis are about over centralization, of power and influence. And these are solutions that work at hectare scale. They work at community scale. And I think when it comes to abundance of energy, food, and labor, and climate repair, there's so much we can do locally. And that's really where I see the frontier of really development, of actually finding these good repair solutions. We've got communities up and down the coast that want to do something and ensure that their communities can continue to be livable for decades to come for the next generation. And so why not start locally? I'm a big fan of community development of this sort that is sustainable and ensures livelihoods and climate repair locally.
Okay.
Yeah, another one, and I think the last part I could answer. It says, to what extent can your technology scale and sequester millions of tons of carbon? And are there simpler variants of the technology that don't require sinking and lifting? And I didn't think that I thought you were just cutting the kelp and you could regrow, not like, or you're dropping the whole platform?
The whole platform goes up and down. We call that moving Muhammad to the mountain. And that is, there's a mountain of nutrients down below. It takes 100 times less energy to do that. A decade ago, we said, you could upwell 1 million cubic meters of seawater a day and irrigate the kelp forest. It turns out that's a lot more solar energy. So these days, we're getting by with some very small, a few square meters of what we call traction buoys that raise and lower the platform. They're very affordable, and we're lowering the cost of those every day. So it ends up being a lot easier to bring the seaweed, which is neutrally buoyant, down to the nutrients than to try to bring 1 million cubic meters of seawater up to the surface.
There are two from Nadia. First is, are there necessary nutrients distributed evenly enough across the ocean to grow kelp at Point Nemo and otherwise all across the ocean?
Yes, there's a wonderful thing about the deep ocean, and that is you have nutrients everywhere in the ocean, just 100 or 200 meters down. And so it's almost like having a ground plane. I'm an old circuit guy. You've got replete sunlight on the surface, and just 100 meters down, you've got all the fertilizer you could ever possibly use. And all we need to do is connect that nutrient with the surface algae to enable a regeneration of life in the ocean and primary photosynthesis. In fact, half the oxygen produced each year on ocean planet Earth comes from the ocean. It's like the second lung of our planet. So if we don't keep our ocean alive, it's our life support system. It's actually what we need to sustain life on this planet.
Okay. And then her other one was, she said, I was under the impression that oxygen losses are primarily related to how solubility varies with temperature. Is that not as large an influence at abyssal depths?
That's a good question. It's a balance. There's gigatons of oxygen. I mean, the source of oxygen is the Antarctic bottom water and the Labrador Current. And that circulates throughout the ocean. The oxygen levels are really quite high in the deep ocean. So you've got to look at the sources and then the sinks. Now, the metabolism and the respiration is pretty darn slow at the bottom. There is a nice concentration of life on the seafloor, but it ends up being there. There is a solubility effect, but as I mentioned earlier, life creates the Earth in its image. And what that means is the life in the biosphere redistributes the distribution of elements, oxygen and everything else is determined so much by life. It's really a bigger factor than the solubility. Yes, when the temperature gets higher, solubility is a bit less. But the key thing is that life in the ocean has a huge effect on the respiration and the photosynthesis that takes place there.
Okay, and then the last one I had, Dan, was from David. He said, Brian mentioned that a warm Earth can only support 1 billion people. Are you familiar with the Georgia Guidestone's reference to a familiar population number? Could we reconcile this with pro-growth?
That's a good question. Well, the good news is it seems like the population is going to be leveling off below 10 billion, which is helpful. I think a soft landing of just, enabling a soft landing of a few billion people would certainly reduce some of the pressures on the planet. And that would be done, with voluntary family planning and other approaches. But I think really there are a number of approaches that we need to work with communities to ensure abundant food security. And this is described in Tony Seba's book, Stellar, with James Arbib. And it really talks about abundant energy, abundant food, and abundant labor. And on the food side, they talk about precision fermentation that we've mentioned briefly. I like to add precision agrivoltaics, which is actually growing food and photovoltaics, vertical photovoltaics, on the same acres at the same time. And then the third one is precision mariculture, of which our marine permaculture is one example. Once you build it, we can continue growing seaweed for decades. No further inputs are needed and no toxic outputs. And so this is an example of a marine stellar technology. And so I would love to work with others around the world to build sustainable stellar communities at community scale that provide its residents with abundant energy, abundant food, and abundant labor. And I think that is the bright spot. Once we get these prototype communities going, we can replicate them thousands of times, and that abundance can pay it forward and enable sister communities to get started as well. So that's my hopeful view at community scale: decentralized abundance and real wealth that isn't measured in dollar terms. It's measured in terms of, for your family, having enough energy, enough food, enough labor, and abundance.
And another question was, is the slide deck available, or maybe?
Yes. In fact, we just did a webinar with Santa Cruz, and we're going to be publishing that video over the coming week, and slides that go along with that.
So on your Climate Foundation website, they can get it? Yes. Links in the description, by the way, to the Climate Foundation website. And also, I think there's a link on Twitter or something like that. So, yeah, you can keep track that way. That would be great. Yeah, certainly very interesting. And a very, compared to a lot of things we talk about on Climate Chat, quite hopeful solution that can scale. And I do like the fact that you're right. A lot of the things we talk about have to be done at mega scale just to start providing value. But if you're providing food and local cooling to a village somewhere in the Philippines or something like that, that could help right away. And then enough people like that, they start doing it. Then all of a sudden you actually have a mega scale solution. So,
exactly. 1,000 points of light or 1,000,000 points of light distributed around the world. That's our hope.
Are you going to be speaking at UCSB?
I would love to. In fact, we're planning next year to do, we did a workshop back in 2019. And in fact, Santa Barbara Channel will be the site of our first year of operation of the pilot. And so we're aiming for those matching funds. Check out climatefoundation.org, and you can dedicate those funds to building America's first marine permaculture pilot.
Because I will require attendance of my children. They're both there.
Wonderful.
Great. Thank you so much for spending time with us, and over the years, by the way, but being a supporter. Oh, wait, Leon, I forgot. Leon had a question. So, Leon, before we go, I'm sorry about that.
No worries. I just brought myself in. Hi, Brian. Great to have you. And I think so. The quote, as I remember it from James Lovelock's book, is that life creates conditions for life to exist. And of course, we are also part of life. So, of course, we are changing the climate. So we also have to be part of the solution. I think that, I really like the presentation. I think it's really great how you bring, in a way, supply and demand together with these nutrients, right? How you bring like Charles always, how you bring the plants to the where the nutrients are and back up to the light. And what are your long-term plans? How you can, for example, get these plants to where they are needed? Like, what are the latitudes they function well in? Which countries are you looking at? Of course, there's I don't know, 50 countries, I guess, in regions where this could be applicable. Do you have a rollout plan for that? And
yes,
because I can imagine that they need nutrients, they need food, they need maybe regional cooling. So
definitely, in the months ahead, we'll have the full hectare, the commercial scale hectare running in the Philippines, and that can be replicated worldwide Panama, for example, really needs to rescue their fisheries because they're facing another upwelling failure with the next El Nino, and this is going to be a serious problem for them. And that represents food security for all their fisheries. Similarly, we're looking to stand up these hectares of marine permaculture off the Australian coast. We'd love to do America's first marine permaculture pilot with matching funds. And in Europe, they've seen a dramatic loss of seaweeds off Portugal, et cetera. And imagine if we put these in the Mediterranean, we could actually restore the primary production of the Mediterranean and perhaps even restore the sardines to Sardinia. Imagine that. So, there's a quote in James Lovelock's Novacine that really appeals to me. And he says, the purpose of life in the universe is to turn sunlight into diverse information. And that can include biodiversity of ecosystems. It can include artificial information with AI. I think that's profound. And I want to lean into that notion of life in the universe, producing diverse information that can lead towards a bountiful future.
Well, thanks for sharing your diverse information with us today. And so I guess we're just collecting sunlight here in Climate Chat and beaming it out to everyone here in terms of intelligence about the climate situation. Thanks for what you're doing and for sharing it with us. And everyone, check out Climate Foundation website, link in the description. Oh, by the way, forgot to say it, but of course, please like and subscribe and share this with others. This is kind of a positive one. So if you have your friends who are like bummed out by everything you tell them about climate change, this is one you can share. And hey, there's some good news, and share them this one as well. So again, thanks for what you're doing, and thanks for everyone for joining us today. And we will see you next time, everyone. Take care.
Thank you, Dan.
Bye.
Thanks, Brian. Thanks, everyone.